SQL, also pronounced SQL, remains the dominant programming language for interacting with databases 5 decades after being created, which is a pretty incredible feat in tech. It's been able to keep this position because of its simple declarative syntax, easily performing common database operations like reading, writing, and deleting data, and its use of intuitive data structures like the table. One of the biggest keys to its enduring success has been its ability to adapt to the major shifts in the data landscape, from new use cases like analytics to the sweeping innovations of the big data and cloud computing age. A common dictionary definition for SQL you'll see everywhere is that it's a programming language designed for managing structured data in a relational database management system. While SQL was initially designed for this system and is still in use today, these definitions fail to capture the significant evolution the SQL language has undergone since its beginnings. So, let's dive into the exciting journey of SQL's history to grasp how this language has transformed into the diverse and powerful tools we have today. The story of SQL starts with this man, E.F. Codd. In the early 1970s, while working at IBM's research laboratory, he wrote several academic papers establishing and refining a groundbreaking framework for data organization and access called the relational model. Prior to Codd, we'd see users interacting directly with a database's physical storage details, needing to know where data files reside on disk, or using pointers to navigate between records. He proposed we should be able to interact with data through an abstraction called a logical model. The logical model he put forward was based on set theory in mathematics and described data as being represented by tabular data structures he called relations. A relation attempts to model an entity from real life, in this case a customer, but it could be anything. Its properties are described by what Codd called attributes, like a customer's date of birth. A tuple is a collection of attribute values that make up a single entity, so one customer in this example. The relation is comprised of many tuples that can appear in any order, and each tuple is identified by a unique key. We can then map real-world relationships between entities by including the unique key of one relation into another relation's attribute. Here we're describing a one-to-many relationship where one customer can have many orders. And crucially, Codd also conceived of a proto-language called DSL Alpha designed to interact with the relational model, which laid the theoretical groundwork for the SQL we still use today. You can see from this screenshot of Codd's foundational paper the beginnings of what SQL would be, and some basic commands you might recognize. Codd's concepts were used by another team at the IBM Research Laboratory to create a prototype relational database called System R, and a programming language for interacting with it called Square, later renamed to SQL, which eventually became the 3 letters SQL. From this prototype, a number of commercial products arose, and because the papers coming out of IBM were widely circulated, other companies like Oracle created very similar systems, complete with their own versions of SQL. These systems that more or less implemented Codd's ideas are what were called relational database management systems. Instead of the academic mathematical language used by Codd, data structures in these commercial systems were given more practical, intuitive names. Relations became tables. Attributes became columns. Tuples became rows. Relational systems were uniquely good at performing what is called online transactional processing, or OLTP for short. This type of processing is characterized by quick, row-level operations called transactions. For example, adding a new customer, or updating a customer's date of birth. This type of work was hugely popular for operational systems, such as banking and financial systems, that wanted the ability to execute large numbers of transactions concurrently in a reliable and consistent way. There were, however, significant differences between the vendor-specific implementations of SQL. In the 1980s, ANSI sought to standardize the SQL language to create a common, vendor-independent set of SQL features. The first standard, SQL 86, given its name by the year it was created, specified the foundational syntax and semantics of SQL. We have commands that perform operations like reading tables, adding and updating data in tables, creating tables, filtering rows, and much more. Transactional systems had been primarily focused on gathering operational data which is crucial for day-to-day business activities. However, it became clear that all the data being collected had a secondary benefit. It could be analyzed to make better decisions and provide insights. To address this, a dedicated database known as a data warehouse was purpose-built to perform analytics. It stored data extracted incrementally in batches from source systems like transactional databases using a process called extract, transform, load, or ETL. It adopted many of the same data structures and terminology from relational systems, including tables, rows, columns, and primary keys, but it used different data models, like this star schema, which is more suited for analysis. Not only that, but the underlying database architecture was optimized for analyzing larger volumes of data, and enhancements to the SQL syntax to facilitate advanced analytics were introduced. In contrast with online transactional processing, this approach to processing data is called online analytical processing, OLAP, focusing on complex data analysis across large amounts of data instead of many row-level operations. The creation of data warehouses demonstrated that SQL was much more generalizable than originally designed. Up next, we continue the story with part 2 and look at how SQL appears in the modern day.